Welcome again, and welcome back to those of us joining us for our second presentation of the day. We want to welcome you all to the 2022 Virtual Viscosity Summit. Thank you for joining us and starting the year with us. So just a reminder, we are now having our presentation from Kraft Heinz. At 11 a.m. Pacific, we will have a presentation from Carbon 3D. We will have a 1-hour break for lunch. And then at 1 p.m. Pacific, we'll resume with the University of California, Santa Barbara, and we'll conclude today's event with a presentation from RheoSense. Before we get started, just a reminder, we encourage you to follow us on LinkedIn, Twitter, and Facebook to stay up to date with all the latest rheological and viscosity applications, news, and updates, as well as to connect with our team, or we can help you connect with speakers after the event. If you do have questions during our presentations, we encourage you to ask them in the chat or the questions panel that you should be able to see from the webinar screen. All of our speakers have saved time at the end of their presentation to answer your questions, so you can drop those as they come to you, and we will answer all of those questions at the end. Now, our next speaker is from Kraft Heinz, Dr. Shamsheer Mahammad. He is their senior principal scientist. Dr. Mahammad earned his PhD in chemical engineering from North Carolina State University, where he studied enzymatic reactions in water-soluble polymer solutions, focused on rheology and kinetics. He's been with Kraft Heinz for over a decade. This is not his first time speaking with us. He was at our first ever Viscosity Summit in 2021, and he is back to speak this year about intrinsic viscosity measurements of food biopolymers. And it is my honor to introduce and pass over to Dr. Shamsheer Mahammad. And Shamsheer, just so you know, before you dive in, I can see your screen, but you are muted. So we want to make sure we get you unmuted before you start presenting.
Okay, thank you. Can you guys see my desktop now?
Yes.
Okay, first of all, let me thank RheoSense for inviting me to present or share some of my experience with Kraft Heinz, how we apply the rheology in food product designs. Okay, my topic will be basically I'll be talking about how we use how we can use the RheoSense Virog Kinesium instrument to measure the intrinsic viscosity of biopolymers, how we can utilize them in a product design. So just to give you an outline, what I'm going to talk is I'll give you a brief introduction of application of rheology in food product design, how we use a rheological fingerprinting in food product design. It's some introduction of food polymers. Basically, it is proteins and polysaccharides, how we can use the intrinsic viscosity measurement, and also particle size distribution analysis using dynamic light scattering. Then I'll show you how we can combine these two measurements to get the molecular weight distribution of the polymers. So basically, if you look at why the rheology, as most of us know, the rheology is the science of flow and deformation of the materials, right? All the consumers what in the food is they wanted a great tasting product, should have a right mouthfeel when they eat it, a very pleasant mouthfeel. That's what you're looking at. So basically, all the sensory perception of our food in our oral cavity is related to how we chew, it depends on how the rheology of the material is. That's why the rheology is so important in a food product design. It's not only we use rheology to select our ingredient, understand what is the right set, the right processing parameters, and what should be the finished product texture that should be there to we use rheology for even measure the texture as well as even the shelf stability of the materials. So any product that you make, you should not have like in a cheese, you should not get a oil on the top or the fat coming out of the cheese matrix, or in the mayonnaise the fat coming, it's not desirable. You should also hold all the moisture and fat within the matrix without any synergies or the oil separations. That's what I'm talking about, the shelf stability of the materials. So the combining both formulation and processing and the product performance in every stage of the entire food production cycle, we use rheology in for different aspects. Yeah, it's very helpful in terms of developing a product at a much accelerated rate, so that once the idea is from the idea to final product marketing, so we can use the rheology and to get the product as consumers want. So this is what is rheological fingerprinting. This is a typical flow curve, that's the viscosity versus shear rate for most of our this mainly for a sauce-like product. This type of flow curves we get, that is a very low shear rate. We have a Newtonian behavior where the viscosity is independent of shear rate. At around 0.01 to 0.03, then the viscosity starts shear thinning. Then it again very high shear rate. It becomes a Newtonian fluid again. So if you look at very low shear rate, number 1 and 2, the mouthfeel texture, when you take a scoop a salad dressing or into your mouth, that's where your texture is related to the rheology at that or the viscosity at that very low shear rate, or we call it zero shear viscosity. Even if you look at sedimentation, the viscosity at the low shear rate is also important to stabilize an emulsion type product like a ranch dressing. So you don't want any flocculations or sedimentation is happening. That the viscosity at that low shear rate is important. So if you go to the number 3 here, that is where the viscosity starts shear thinning. If you have a ketchup, and when you squeeze the ketchup, with the viscosity is required, you should have should not have very thick viscosity. You should not be able to squeeze it out of the bottles. To have an optimum level of viscosity so that we can take it out of the bottles. That's why the shear thinning behavior starts. That's number 3. For squeezing, spreading, and scooping, that's the viscosity. In that range it comes for the shear rate. Number 4, if you look at the flow under gravity, 5 is for the pipe flow in the range of number 1 to 1000 inverse second as a shear rate. Even for the number 6, the emulsification, you need a very high shear rate to emulsify. That means create a very fine droplets of oil in your emulsion. At the same time, if you see when you're mixing an oil in a other matrix, like in the protein where you used as a stabilizer, or the starch, carbohydrate where you want to stabilize your emulsion, in that when you're applying a high shear, the viscosity goes down. At the same time, you need a high shear rate to get the emulsification. There's an optimum level of shear rate is required. You get a fine fat droplets. At the same time, you have a right number of viscosity. As you remove the shear rate, there is sufficient viscosity to keep it stable too. If you look at very high shear rate, that's number 7. This is the shear rate that you usually see if you are spray dyeing to get a powders, like in the cheese, mac and cheese powders, where the cheese sauce is initially made, then it is spray dried to get that powder, where it is supplied. Very high shear rate is required. So the optimum, very good performance of the spray dryer, you need to have the right viscosity at the very high shear rate. Next, here I can give you an example. If you look at traditionally people use a different kind of viscometers to measure the viscosity at one particular shear rate. Many times we don't know what shear rate we are using, like in the Brookfield viscometers. We measure the viscosity at a particular RPM of the particular using particular spindle, and measure it at a particular RPM and get the viscosity. There's a Bostwick consistometer that's typically used for a ketchup, measuring the consistency of the ketchups. And we also have Bostwick on the Oswald viscometer. It's a very thin fluid, like by gravity, how long does it take to move from one position to other position. See that from the time we can calculate the viscosity of the materials. So if you use a single point measurement for the same product, what you may end up is you may end up in a three different designs. What I'm trying to say is, so this single point measurements are good as far as you have finalized your product, processing parameter, everything. Then you can use it as a single parameter only for quality control purposes. But when you're in the design stage, you need to have entire flow curve so that every experience of the all the food industries, our purpose is to make a product that consumers will like. So this whole curve will give you the viscosity at a different levels of consumer experiences, as I explained earlier, from the mouthfeel to processing, as well as the spray drying, all those things. So getting entire flow curve matching up is very important. That means you have a control product, you wouldn't like to have a design a product compared to a particular flow curve, then you develop a product and get the right formula to get that product to that level. See, in this case, same product, you can see here the viscosity in a different, if you use a different type of viscometer, you get three different values. You end up using the different, coming up with a different product. Okay, now this is another example, as I explained earlier, just to give you, the entire flow curve needs to be developed in the food product design. Here, you can see the Brookfield viscometer range that typically we use a lot for the quality control. It comes in the range of 1 to 100 shear rate, depending on the RPM or the spindles that you use. So let's go to the food polymers. Basically, if you look at the picture on the right, is a confocal microscopy of processed cheese. Here, the red color uses the protein, black is starch, and the fat is blue. What you can see here, there is a entangled network of proteins and starches where the fat droplets are trapped inside these polymeric matrix. And also, anyways, quite a bit of moisture is also there in this processed cheese. Even this starch traps the moisture also. It prevents the mobility of the moisture within the cheese matrix. So basically, in the proteins in the food, we have dairy proteins, animal proteins, or the plant proteins. These are the main proteins. Polysaccharides, there's a lot of natural polymers available, coming starches, galactomannan, glucomannan, chitosan, pectin, carrageenan, and etc. So another thing is functionality of these food polymers depends on their size, molecular weight, and environmental condition. If you have those polymers, specifically the proteins are very, very sensitive to the pH, salt, or the concentrations within the environmental conditions that I'm talking about. The proteins, basically in the native stage, they form in the dairy proteins, basically the casein proteins, they form a micelles. So when you heat it up, they open up and create a extended polymeric molecules. As you open these polymeric chains, they start, even depending on the temperature, it can even cross-link or entangle with a just simple physical entanglement. That's how in a processed cheese this network is formed. So this will increase the viscosity that will trap the fat inside those in the cheese matrix. And also in the cheese matrix, this proteins acts as the emulsifier. So to stabilize the fat droplets, you need to have the proteins. So also the proteins are polyelectrolytes because of these amino acids. It's a polymer of amino acids. Depending on the pH or the salt condition, the net charge density on the protein molecules will vary. That will also influence its functional properties in terms of for their stabilizing effect or texturizing effect, or texturizing, I mean here the viscosifying effect also. Another thing is exposure of protein to temperature. When you're processing, definitely we have to apply a lot of shear, either through the pumping or in your cooking process, the shear is applied. Shear is also important for denaturing the protein. At the same time, you should not be over shear or expose the proteins to higher temperature for a prolonged time. It will over cross-link and more undesirable texture can also form. So there's an optimum level when you're processing. It's very important to understand the rheology of the materials, how it get influenced by the environmental conditions. Next, polymers are the polysaccharides. The starches have given you some structures. The starches is basically that comes in two different forms, the amylase and the amylopectins. Amylose are linear polymer of glucose molecules, where amylopectin has some side chains. Starches are used basically to immobilize the water in a food matrix, basically because of their high affinity towards water. Also, the high viscosity can also used as a stabilizer, so to prevent any oil droplets or fat droplets in the food matrix, to prevent them moving around. We have galactomannan. The examples are GOR, tarragon, fenugreek, locust bean gums. They are basically polymers with a mannose backbone chain with a galactose side chains. The mannose to galactose ratio changes depending on these natural polymers. GOR, these have a different galactose to, that's where their difference is. So depending on the galactose to mannose ratio, their stabilizing and the viscosifying effect also changes. And another one is the glucomannans. One of the examples is a konjac mannan. They are basically mannose. They have a mannose backbone with a glucose side chains. Pectins and the xanthan, these are the ionic polymers. The pectins are an ionic polymer of galacturonic acid, where xanthan is ionic polymer of glucose, mannose, and glucuronic acid. They're also very sensitive to, since it acts as a polyelectrolyte, they also change their behavior, or the rheology of the material will be affected if you change the pH or the salt concentration in the molecules. Another good aspect of xanthan is they also have, it's quite a large molecule. They also have a tendency to interact with other polysaccharides, like in some of the applications, people use mixture of xanthan and locust bean gum to get a synergistic effect, so that you don't have to use, you can optimize the level of this polysaccharide. You can get a similar rheology by combining these two polymers at a certain lower levels, so to get a synergistic rheological effect. So let's so basically, as I mentioned earlier, these polymers provides the basic framework in any food matrix. So rest of the things are trapped inside, like the other molecule, the flavoring molecules, protein, not protein, the water and the fats are inside these polymeric network structures. It's very important to understand these their structure and the molecular weight of these polymers to get the right texture that the consumers like. As mentioned earlier, not only for texture, mouthfeel texture, of even the stability of the materials, how long it can stay stable either in a refrigerator or on the shelf. So these polymer, how these polymer, what type of polymers that we are using and how it are structured in a fruit matrix is very important. So let's how we can use the intrinsic viscosity measurement. Intrinsic viscosity is a measure of solids contribution to the viscosity of a solution and defined and is equal to the specific volume of the solids in the solution. From Einstein's equation, we know that the specific viscosity is equal to 2.5 times the volume fraction of the solid. So from that we can say if you change it to pi over 6 d cube as the volume of one individual particles in the Avogadro numbers, you can eventually come up with an equation. Intrinsic viscosity is 2.5 over sigma, that is a particle density of the materials. That is the one particle, how much mass is trapped within that one coiled chain of the molecule. So from that you can calculate, once if you know the diameter of the size of the molecules, the polymer molecule, if you know the density that can be estimated from the intrinsic viscosity, then you can get the molecular weight of that. That's the approach we are taking instead of traditional gel permeation chromatography or anything. Because there's a lot of challenges even using the gel permeation chromatography. When you have a very large molecules, it's very challenging to get a very consistent results in a gel permeation chromatography. That's why we are taking a very simple approach and very effective approach. Intrinsic viscosity measurement, this is we used recently, we acquired this instrument in our lab for measuring the intrinsic using the Rheosense Viroc Initium instrument, where we use the very dilute concentration of these polymers to measure the viscosity at different levels, and then from that we can calculate the relative viscosity and the intrinsic viscosity of the materials. The beauty of this instrument is the accuracy and this sensitivity at very low viscosity range. It's very difficult, even though we have quite a bit advanced rheometric capabilities, but for the low viscosity range, this Viroc instrument gives the much accuracy and precision. Other thing is, to give you another advantage of this instrument is for low viscosity food materials like coffee and the beverages, so the viscosity doesn't change much. But even the viscosity is not very low, but in this case of when the consumer feels the difference. So even the coffee may have a viscosity within the range of 1 to 2 centipoise, but consumers feel the different variety of coffee different. So depending on what is there, what type of polymers are there when you're brewing, it comes into the coffee. But the intrinsic viscosity measurement can differentiate such type of mouthfeel texture that consumers feel. So next one is, as I mentioned earlier, in this case, molecular weight can be calculated if you know the particle density as well as the particle size. What we did is for measuring the particle size, we used the light scattering. And the light scattering is when low energy visible light interacts with the matter, the incident light induces a dipole in the electron cloud which oscillates at the same frequency as the incident light. From the light scattering intensity versus time, we can estimate the size of the particles or the size of the polymer molecule in the solution. So there is in the GPC, generally it is the static intensity is used, or static light scattering is used, where it is a time averaged intensity versus time curve of the light scattering. For the dynamic scattering, this fluctuation in the light intensity is used in measuring the entire particle size density, particle size distribution of the molecules. Because this scattering, the fluctuation is arising because of the Brownian motion of these particles in the solution. So that can be utilized in estimating the molecular weight distribution, particle size distribution of the polymeric molecules. So basically, in the Rayleigh isotropic elastic scattering is used in estimating the. This is the equations that has been we use when converting the intensity to particle size distribution. This is the from the light scattering. That's the fluctuation in the light intensity versus time when you get a correlogram. From the correlogram, you can connect it to from the Boltzmann's Stokes-Einstein's equation. You can calculate the hydrodynamic radius of the particle. So this is the if you see on the this measurement is done at a scattering angle of 173 degree on the top left corner. We have a correlation coefficient versus time data. So that data is converted into the diameter using the equation that I showed you earlier. You can see the equation here, the diameter versus the light intensity. From that, you can some mathematical manipulation is needed to convert the intensity versus diameter data into a volume fraction versus diameter data. So that is what is mainly required when I talk about next about the calculating the molecular weight distribution. From the volume fraction versus diameter data, you can also calculate the number fraction versus the diameter here. So here in this graph, this is the sodium caseinate. Basically, it's a milk protein. It has 20 to 25 kilodalton is usually its molecular weight range. In this case, you can see the we measure the intrinsic viscosity using the Rheosense, which has intrinsic viscosity came out to be 0.0619 deciliter per gram. And the diameters, the particle size on the top left corner, we have a particle size distribution measured using dynamic light scattering. And the bottom left corner, we have the molecular weight distributions. You combine all this data and you can get from the particle size from the dynamic scattering, Rheosense intrinsic viscosity. From that, you get the particle density. From that, use that to calculate the molecular weight distributions. So based on this, the mean molecular weight what we got was 23,545 daltons. So comes close within that range that we haven't yet validated it against gel propagation chromatography yet, but this is quite close. That's good enough for this estimation. The mean particle size came out to be around 46 nanometers for the sodium caseinate. So this is another, to validate this model, we also had some standard dextran molecules that purchased from the from Fisher Scientific that we used here to validate the model here. So the one is a low molecular weight dextran. Dextran is a polysaccharide a polymer. It's a linear polymer of glucose molecules. Here it is 10 to 15. It's a low molecular weight dextran. You can see the intrinsic viscosity measurements, the particle size measurement, and the molecular weight, estimated molecular weight. Here we got slightly higher than what we expected, 10 to 15. Here 17,148 is a mean molecular weight. It's a weight average molecular weight, 17,000. Particle size is around 14 nanometers. Intrinsic viscosity is around 0.13 deciliter per gram. So now it is a higher molecular weight range. This is a medium. I have one more data. It's 100 to 200K molecular weight. You can see the intrinsic viscosity, particle size, and from that we calculate the molecular weight. It comes within the range that we expected here, 124, 202. Mean particle size around 24 nanometers. Next one is the 200 to 300K molecular weight. The intrinsic. So again, it comes within the range that we expected. So it looks like our model works quite good. Finally, to combine all these curves, all three dextran molecules, if I combine them together, you can see the intrinsic viscosity versus the molecular weight that estimated. If I draw a curve, you can get the power factor of 0.45. See, basically, if we look into Markov-Hines equation, that is intrinsic viscosity is molecular weight to the power either power 0.5 to 0.8. Depending on the type of the polymer, we are getting very close to, this is what we expected, it should be around 0.5, because the linear polymers should be acting as in a water solution. Water should be a theta solvent for these molecules. It should have around 0.5. So, but it's coming very close. So basically, to summarize, what I talked about is there's combining intrinsic viscosity with the particle size distribution. We should be able to measure this molecular weight distribution of the polymers. So that's all I have. I will be happy to take any questions. Thank you for listening.
Thank you so much, Shamsheer. So if anyone has any questions, please drop them in the questions panel, and we can get all your questions answered. All right, we have our first question, and it is, have you tried to measure other types of polymers, such as polyacrylamide derivatives?
No, this polyacrylamide derivatives, obviously the food industry, we have to use all the natural polymers, proteins and polysaccharides. We generally don't handle with any synthetic polymers.
And are there special techniques or equipment required to do intrinsic viscosity?
No, we use the Vero Kinesium, that's a Rheosense instrument for the intrinsic viscosity. Basically, what you do is viscosity measure at a few concentration. From the plot the curve, viscosity versus concentration data. From that, you can calculate the intrinsic viscosity.
And are polysaccharides autoclavable? How are they sterilized? Do you check their integrity by rheometry?
They're quite stable polymers. We generally make a solution. Yes, there may be a microbial disintegration can take place, but we usually make a solution and immediately make a measurement. If you're not using, we can use some biocides and keep them stable. Other than that, there's no disintegration, or they're quite stable molecules, these polymers. Yeah, but rheometry, we can use it where typically for the very high concentrations, we generally use it for, but in this project, the purpose is here to validate their molecular weight distribution. So we don't have to use for higher concentration, very dilute concentration. It's less than 0.1% solution that we were using for this.
Wonderful. So this one's a little longer, so I'm going to read it slowly. Is what you described referred to as a type of viscosity light scattering method? I've come across a similar tool for the determination of the core size of polymer-coated nanoparticles and was just curious if these tools can get similar analytical results.
Definitely, it can get. You can use it for if you're if it is a polymer mole. If you're interested in the molecular weight distribution, definitely you can use. If you just want to know the size, you can either use the intrinsic viscosity or use the light scattering. Either can be used. Yeah, and from the intrinsic viscosity measurement, this is proportional to the equation I showed you, proportional to the volume fraction of the materials. So intrinsic viscosity give you an average idea of size of these nanoparticles. So, and also light scattering is a more better way to get the whole distribution of the particle size. Yeah, this dynamic light scattering you can get from 1 nanometer onwards. The minimum you can get is 1 nanometer in the dynamic light scattering.
And then since you are running specific shear rate to extrapolate intrinsic viscosity, how much variance do you get if you're running various shear rates, more akin to the process being run, i.e. trying to match intrinsic viscosity to the molecular configuration?
Oh, okay, but since that's a good question, actually, we are using the very, very dilute concentration. At that concentration, there's a total Newtonian behavior of the materials. So yes, to get into the right sensitivity of the instrument intrinsic viscosity measurement, you have to use a very high shear rate. But if you measure it within the instrument range, if you measure the viscosity at those high shear rate, you get a Newtonian behavior. So this is a very, very small concentration. This material behaves Newtonian. That's very important here. So there's no shear dependence on the viscosity. Here we are measuring at a very low viscosity. From that we calculate the intrinsic viscosity measurement.
And someone's asked, how dilute should the solutions be for intrinsic viscosity measurements?
Can you repeat the questions? Sorry.
Oh yeah, how dilute should your solutions be for intrinsic viscosity measurements?
Yeah, the good question is, yes, you have to use the concentration in such a way that your the curve, the viscosity versus concentration curve becomes a linear one. Okay, so if it is start, yes, after if you go to the what in the rheology we call it overlapping concentration, after that the molecules, that line starts bending, that becomes more of a power law equation starts coming in. So you have to use a concentration in such a way that you get a linear, a straight line, that is viscosity versus concentration is a straight line. You should not, yeah, for in our cases, we found that less than 0.1%, the viscosity, very straight line, is a straight line.
And at what concentration do you believe a food grade quar becomes a random coil instead of an assembled mass? And how does time affect this process?
That's a good one. As I explained earlier, if you go for some of the molecules, it depends on what is the polymeric, what is the molecular weight of your polymer. See, if you're a starch, it can go up to a little higher concentration. For the cigar molecules, you may start seeing the more overlap concentration, not a random coil here. So you can see more of a overlap between the polymers, even if you go more than 0.1% concentrations. So that's why I said you have to choose your concentration in such a way that you get a straight line, viscosity versus concentration.
And they are still rolling in. Someone's asked, I was told intrinsic viscosity requires extreme repeatability. Do you have any tips on handling and making sure measurements are good quality?
I have a very, I can tell from the Virhoc instruments, I had a very good experience here. So my you get a very high repeatability in this less than 0.1% repeatability I get in this measurement. But yes, getting this type of measurement if you're trying to do it in a rheometer, it's very difficult. But I think we can get this repeatability in the Virhoc Initium instrument. Yeah, this is a simple capillary rheometer, viscometer here. So getting a repeatability is not an issue as far as you make your solution consistently at the same concentration and there's no separation, your solution is quite stable. That to make sure that it's stable, then you can get there should not be an issue getting the consistent results.
And someone who is a VROC user as well says, I've used clarity to calculate intrinsic viscosity. Do you use that as well?
Clarity, I didn't get what you mean by clarity.
Clarity is the RheoSense software that you can pair with the VROC Initium 1 Plus to calculate your intrinsic viscosity for you.
Yeah, you can do that too, but I use the Excel spreadsheet, take the viscosity versus concentration data and calculate using the, yes, I never tried that. Yes, I have that instrument software, but I used Excel spreadsheet for calculating this.
And when you prepare your solutions, do you make a stock solution and dilute it, or do you make each concentration separately?
Yeah, that's a good question because usually I make some of these solutions I can make up to 1%, then I dilute it. Some in cases, some polymers don't dissolve at that level because of the very high molecular weight involved. So like a carrageen, and you cannot even go up to getting a 0.1% solution itself is a difficult thing. Yes, I make the concentration in such a way that it is soluble and you get a very clear solution. Yeah, it all depends on what type of polymers you're using and what is your environmental conditions. Like for the proteins or for electrolyte, if you're using a buffer solution, it contains some salts. It all depends on its solubility. So the protein solubility can be changed by adding salt, type of salt, something like that, and the pH of your solution.
And if anyone else has any questions? Yep, another one has come through. Is clear solution a must for measurement?
I leave it to the RheoSense people to answer this question. I don't think so. It's is it as far as the stable, you should be able to get it.
I will see if anyone on our team who's signed on wants to chime in on that question quickly. Yes, one of our specialists says the solution does not need to be clear. No, clear solution is not a must for measurement. And I'll give everyone just 1 or 2 more minutes to drop their questions in the question panel. See if any additional questions come in before we thank Dr. Mahammad for his presentation today. So Shamsheer, we did have one question, and I answered this in the first presentation, but I will, let you address this as well. They asked if someone has asked if the presentation will be shared or the slides will be shared. And as I said in the first presentation, we do share the recordings of our speakers. However, sharing their slides is speaker dependent, as everyone is under different stipulations. And so if they are able to share, that is something that can come, but not something all of our speakers will be doing. We had one more question come in that said, do you have polymer applications using intrinsic viscosity?
This is the polymer applications in the food polymers. The food major basic framework of our food matrix is the polymers, like proteins and polysaccharides are polymers. That's what we are using here. The molecular characterizing their molecular weight distribution is very important to get the right food texture and the stable texture that we want in the food products. That's what we are doing, but we don't use any synthetic polymers in this case. I didn't have a chance, never had a chance to. Yes, we have our packaging materials may be using the polymers, but in our lab we don't handle any sort of organic solvent. It has to be any food grade materials only that we use in our lab. Yeah, but this can be used for any polymers. It's not only for natural polymers. You can use for this technique can be used for any synthetic polymers too.
Wonderful. Well, I would like to thank you. Oh, nope, got another one coming in. How can you verify if the polymer has fully hydrated or dissolved?
Yeah. One of the thing I could suggest, my suggestion, what we usually do is it is a total, if it is completely dissolved, is to verify make the viscosity measurement in a couple of times at different time levels and see is there a change in viscosity over time. So if there is a change, means it is not fully stabilized. And also if it is very high concentration, there is also maybe a sedimentation happening. You can see at centrifuge it at very low RPM and see if you see any sort of separations. But if for this intrinsic viscosity measurement, very dilute concentration, you should get a very clear solution. And at least for the natural polymers, these polysaccharides, you should get a very clear solution. There's no turbidity or anything. It is visually you can make sure that it is clear and fully dissolved.
Wonderful. Well, Shamsheer, thank you so much for your time today. Thank you for such a wonderful presentation. And we are going to take a brief 12-minute break before our next presentation. Shamsheer, is there anything you wanted to add before we conclude this session?
Yeah, thank you. Thank you all for listening, and then thank again Rheology for inviting me to present my work here. Thank you again. If you have any question, you can connect me on the LinkedIn.
And as I did in the our first presentation, I will go ahead and drop Dr. Mahammad's LinkedIn, the link to his profile into our questions panel so everyone can see. and we'll let everyone go ahead and connect with him directly if they have any questions. So I have connected it in the chat and the questions panel so that everyone can connect with you. And Shamsheer, thank you again so much. It's always a pleasure to have you presenting